So let's begin with a word of prayer. So, dear Heavenly Father, we thank you for this morning. I thank you for these students. I just pray that you be with us today. Help us to just review whatever they need to before the test, that we'd be able to understand whatever it is we didn't understand on the quiz, and that you just be glorified in this time that we have, Lord. In your name I pray. Amen. Oh, I almost forgot. Take this thing out for a spin. Where's it? Whoa. Come on. Stupid. Come on, get in there. Probably Walmart. What's that?
I left the colored lamp.
The colored lamp. Yeah, but
Bright
it
and shiny and beautiful.
it made that like a blurry thing. Of course, now I've added a shadow, but oh well, we'll get over it. I can make shadow puppets. Yeah, it's not one of my skills. Anyway, so any questions about? Do I have all your quiz twos? Thank you. Thank you. All right, so let's start at the beginning. Well, that's weird. The math secretary has sent me an email about Taylor's multinomial. I mean, the one thing that's true about a math secretary is they almost never send you an email about math. So it's very disturbing to me that I was just sent an email about math from the math secretary. Like, what's going on here? I don't know. I'm not sure what that means. Yeah. Okay, here we go. Come on. It's okay, I'll just write it again over here. So, problem 1, did you guys see how to do that one? You can go ahead and turn the lights back on. Sorry. I'm not really using that per se. So problem 1 was actually just kind of a calculus 2 question, right? So how would you integrate e to the sine z cosine z dz? Well, you make a u substitution. That's what you do. I mean, this is the integral of e to the u du. That actually, if you go back and think about all the things that made u substitution make sense in calculus 1, they still make sense here. We still have chain rule, and that's really what the u substitution is based on. So you still have, basically, and I mean, I suppose the proof is in the pudding, whatever that means. I don't know, but the point is that this is definitely an antiderivative, right, of the integrand. So if I'm integrating from minus pi I, was it, to pi I, e to the sine z cosine z dz, well then all I got to do is take my handy dandy antiderivative and use the fundamental theorem of calculus for complex integrals, and there it is, whatever that is, right? So it's e to the sine pi I minus e to the minus pi I, right? Oh, yeah, thanks. And then let's see here. Let me put this stupid thing away. It's not helping. Something funny with that today. All right, and then, so e to the sine pi I is what, you know? Mm-hmm. Oh. Oh. Well, good. I haven't posted the solution yet, but what I have in my solution is just nonsense. My goodness. So you say that's what, sinh?
I sinh pi.
I sinh pi. So that's e to the I sinh pi minus e to the, what is it, minus I sinh pi? Yeah? Sinh is odd, so you pull the minus out. And then what? That is 2i times the sine of the sinh of pi. There you go. No? I have to go for more diffuse light. This thing is like, it's blinding me. Here. I don't know. Nothing. There's no fix to this stupid room. All right. Burn it. I think other things would be in the way of that.
Wasn't caught on video, right?
Oh, what?
Well, you said it, so.
Oh. Yeah, but we can't be sure who said burn the room, Lorenzo. But we'll just never know. Let's see here. Does that make sense? So what I did is I divided by 2i and multiplied by 2i. The divided by 2i I'm always using, this is important to remember as we work on calculations, explicit calculations. This is one of your lifelines, right? You need to know this. Without too much thinking, you should know that. All right, what the other one? The other one, how would you do this without integration by parts? E to the z cosine z dz. What was the idea there? I mean, both of these problems are kind of like somewhat disconnected from most of the things we've been doing. I just wanted to draw your attention to these calculations because I think it's easy to lose track of the stuff we did before test one, right? And this would really kind of more fall in that realm, except that we weren't integrating back then, right? So. And so what you can do is you can say, well, that's really the integral of e to the 1 plus I z plus 1/2 integral to e to the 1 minus I z dz, and then just make a substitution. Do a u equals that substitution, and the w equals that substitution, and out pops 1 over 2 times 1 plus I e to the 1 plus I times z plus 1/2, well, 1 over 2 times 1 minus I e to the 1 minus I. And then, of course, you could finagle that and recast it in terms of sines and cosines and Cauchys and sinh, but that's the main point. I mean, the larger point here, one of the things I'd like you to take away from this class, which is really, I think, more an aspect of algebra than complex analysis, is that there really is, in some sense, no difference between sine, cosine, exponentials, and Cauchys and sinh. They're all just kind of part of the same function in some sense or another. I mean, they're all, you can get from one to the other, and they're all mixed together. They're really part of some more general idea, right? Anyway, any questions about future problems then? I'll just stop there and leave it to you guys. What would you like to know about? Problem number 2. You don't seem overly enthusiastic, so I'll just keep going. Problem number 2, exact implies closed. What was exact? Omega is exact means it's equal to dh for some h, right? And that implies closed. Why? What was closed? Closed was if omega is equal to p dx plus q dy, what do we have? Qx is equal to py, right? This right here is what we mean by closed, right? And so this, if it's exact, and of course all of this is done with respect to some domain, right? Some subset of the complexes. So the reason exact implies closed really was just that the second partial derivatives commute, right? So this would mean that P is equal to hx and Q is equal to h sub y. So therefore qx is equal to hxy is equal to hyx is equal to p py. I guess I should probably, in terms of ordering of derivatives, put these the other way around. Fine. Okay, so indeed exact always implies closed. How about the other way around? No, the other way around is not true, right? Closed only sometimes implies exact, right? There are topological obstructions. We did prove that if we have a closed form on a star-shaped region, that implies it's exact, right? We proved that. However, we also looked at the example. We looked at this example, omega is dz over z, and we saw that the integral around, for example, the unit circle was what? It was 2 pi I, but omega is closed on the punctured plane. So there's an example of a closed form which is not exact. Now, why does that mean it's not exact? What was one of the things we had about exact forms? Exact implies what? Path independent implies integrals around loops are 0, right? So you'd like to know that, right? Exact implies path independent, implies integral around loops. In fact, these are if and only if, provided that they're true for all loops and for all possible paths in some domain, right? There's more fine print there. We should go back and look at the notes to have the complete statement, but this is a heuristic, yeah? So the fact that that integral is not 0 and yet it's closed means that, there's an example. Closed does not imply exact. Unless, of course, we have star-shaped or simply connected. And as you know, the puncture plane is not simply connected and it's not star-shaped because the origin missing is what? So here's a picture of C with a puncture plane, right? So if you're missing this, you pick any point, right? Any point you make the star center. It's clear that there are points you can't get to from that with line segments, right? Because you can always go to anything on the other side of the origin, and there's just no way to get there with a line segment because you have to cross through that point where you don't have. So the puncture plane is not star-shaped, right? There's no star center. But on the other hand, if we throw out a ray, as we know the slit complex plane is star-shaped. Questions?
What is the difference between, it isn't related to this necessarily, what is the difference between analytic and holomorphic?
Analytic is a word that Gamelin has been using to mean complex differentiable and with continuous complex derivative. I believe analytic means holomorphic for Gamelin. So I think they're synonymous.
That isn't always the case.
I think that's always the case in Gamelin, that analytic means holomorphic.
But for other writers, that is not always the case.
Oh man, I don't know. If I think about all other writers, I don't know for sure. It's hard for me to say. For us, I mean the same thing. But I tried not to say analytic up to this point. I've just said holomorphic, which means what? To be precise, holomorphic means that at each point in the domain under consideration, there is some open disk around on that set on which the function is complex differentiable on that open disk. So you have complex differentiability on open neighborhoods of each point in the domain if it's holomorphic. Now, I think holomorphic on star-shaped domain also implies integrable. Now, integrable means that you can find an antiderivative for the function over the whole thing. And so the function 1 over z, for example, f of z equals 1 over z is holomorphic on the punctured plane because at each point right? At each point in the punctured plane, you can, right here, certainly you can find a little open set around that on which one over z is holomorphic, right? It's complex differentiable everywhere except for the origin. But it's not integrable because, well, you can't. If you could find an antiderivative on the whole thing, then we wouldn't have had this happen, right? Because if you integrate around a loop, you should have h of, if this is equal to, basically if this is equal to dh for some h, then if you go around a loop, then h of the starting point, h of the ending point minus h of the starting point should be equal to 0, but it's not, right? Which means that, in fact, you can't find a function whose derivative is the 1 over z function for the whole punctured plane. But on the other hand, we can pick any branch of the logarithm, right? Log sub alpha of z, if we ddz that, differentiate that, we get 1 over z, right? But that's on what? It's on the slit complex plane where we're throwing out the ray at angle alpha, right? It's just one ray, but it keeps the integral non-zero, right? I mean, that's... All right, here's the two ways I had in mind for this one. I will... Oh, no, I haven't... I'm a very bad cameraman. Oh, that's going to be hard to see.
Make them work a little bit.
Make them work a little bit. There was e to the cosine z dz integral. There's the closed implies exact. And then we were talking about this one over here. And then there's that. Oh, well. Sorry, folks. That will be... Well, anyway, Michael decided to drop the class, so I guess everybody who's here is here. Let me erase this. It's distracting. And if you could hit the light in the back now, that'd be good. Thank you. All right, so there I said integrate the square root of z minus I two ways. So the one way to do it was directly from the definition. So from the definition, it's important to notice that the square root here is the principal square root, right? Unless we say otherwise, square root denotes principal square root for complex problems, right? So you just find a parametrization of the half circle, which of course is I plus 3 e to the I theta, right? So so there it is, 3 e to the I theta plus I. That's my parametrization of z. And then when I take dz, I get 3i e to the I theta d theta. The i's cancel in here, and you can pull out the square root of 3, so you get 3 square root of 3i e to the I theta times square root of e to the I theta. But that's principal square root, so the question is, how does that work? And because theta is between plus or minus pi over 2, that means that the principal square root indeed just divides theta by 2 in that range. So it's the way the square root works on e to the I theta here is simply to divide the theta argument by 2. You got to think about that, though. If we had a different range of theta, then something would have happened here, right? It wouldn't just be division by 2. It might be a shift or something. So there's an important thought process there. But anyway, once you've done that, you get 3i theta over 2, which of course you can integrate like so, 2 over 3i, and then evaluate from here to here. But I think that if I haven't made a sign error, and I've made a sign error somewhere in here. Do you guys disagree with my result here? Nobody got this far?
I got what was positive, but it wasn't that.
Really? Is there a particular step you disagree with? Well, anyway, that's what I got. So you see what I did? I did this trick again. I multiplied by 2i, converted this to a sine, because sine has, 1 over 2i. So to get a 1 over 2i, multiply by 2i. 2i over 2i is 1, of course, and then the 3's canceled. And that's what I got. Now, I got the same thing by my other method, but with a sign difference. So I'm making a sign mistake here somewhere, like a SIGN. So the other way to do it, of course, would be just to write down an antiderivative, which you can do, I believe, the 3/2, and that's a principal 3/2 root again. And so if you differentiate this, you get back the principal square root of z minus I. And so when I evaluate that from minus 2i to 4i, which I think is right, because the half circle, right, goes, do you guys agree with that? I mean, the half circle looks like that, yeah? Oop. So we go from here to there, so I should take my upper integrand my upper limit should be 4i, my lower one should be 2i, minus 2i. And I'm making some mistake in here somewhere. I'm not sure where yet. I couldn't find it when I was working it out, and I don't know where it is. But there's some mistake in here, I think. I think that one's right. I think this one's wrong, if I had to guess, because I end up with an extra minus. See, I got a minus e to the pi I over 4, and then plus this. So that would be minus the sine of 3 pi I over 4. So again, I'm not sure where the sign error is just yet. Hopefully I'll find it today as I look at it again. I mean, if you guys see it, speak up.
Can you scroll further down to
This one?
like in the original column?
Yeah, it's counterclockwise oriented, so it's definitely going on the positive half plane. That's implicit from this right here, e to the I theta. If I had e to the minus I theta, it'd be the left half plane. I don't know. Problem 4, I hope you guys got. Do you guys get this? We've had some trouble finding these, so you got it? Yay. Person I won't name by name. No? This one? Oh, yay! All right.
To my vindication, the last problem and the last homework, Daniel said I did it right, even though it was completely different than your solution. So
Oh, really?
I don't know what that means, but
That means that there are, in fact, infinitely many fractional linear transformations that take a half plane to a half plane. There's, in fact, a whole group of transformations. Like, I found problems in my book of Russian problems that are of the form, find all fractional linear transformations that take this half plane to that half plane. And you can find a parametrized family of transformations which do such. And if you think about it, it's not that surprising, because how many different ways are there to map the boundary to the boundary of two half planes? You pick any triple of points in the same order, any triple of points in the same order, that will give you a fractional, that defines a fractional linear transformation, or in the older books, as they call it, bilinear transformation, which is an unfortunate term, that will map the half plane to the half plane. But that choice of the triple is like, I made a choice, right? You guys were like, well, how did you choose that? I don't know, it's just my choice, right? Well, you chose differently, so you got a different one, but it doesn't mean it's wrong. So when I'm checking those, if I have a question like that on a test, what I do is I don't assume you're wrong. I plug in a point. And If when I plug in the point, it spits back out what it's supposed to, then I know you did it right. Like if you say that you're mapping 2 to 3 and 5 to infinity and whatever to whatever, then if I plug those in and that happens, then I know you did it. And if they don't, well, So check your answer and grade it for me. All right, so anyway, the larger point here is that it's possible to do this, right? Because it makes sense because we're looking at 3 points on the boundary of the half plane, right? The real axis is the boundary of the half plane, right, that we're talking about. So it stands to reason that because of the more general theorem that if you're going from these 3 points to these 3 points, right, then there is something of the form AZ plus B over CZ plus D that will do that. That'll map a Z over here to a W over here like that. Now the cross ratio you could do it with, but I would encourage you guys not to be a slave to the cross ratio. Goodness gracious, it is so much easier, so much easier, especially if there's an infinity to capitalize on that. Infinity or 0 should be used. Infinity, if you're mapping to infinity, whatever you're mapping to infinity, you should do Z minus that to get that happening, right? Because you want the denominator to be 0 in order to get the infinity. On the flip side, if you were mapping from 0, to 0, then you could put like Z minus 1 upstairs, but that wasn't the case here, but if it was. Of course, the cross ratio will work, but, Problem 5. This one's hard. Yeah, this one required a little bit different thinking. Let me start with basically the idea is this, as I see it, is basically it's a translation overlaid with a sector. So what I want to do is to think about moving the 1 plus I to the origin, right? So that says I should look at something like the argument of Z minus 1 minus I, all right? And the reason I use minus pi over 4 is because if you can just think of this as being the origin then, minus pi over 4 is right in the middle here, so that should make the formulas come out pretty nice. And that's the one thing you don't have is minus pi over 4. So you want to use the argument which doesn't have that angle in it. So, is this the only choice? No, of course not. You could choose any branch kind of in between. There's infinitely many different arguments you could have used. But I used this one. That said, when you do get back to the level of real notation, we should all have the same answer. It's not like what we were just talking about with the fractional linear transformations where there are genuinely different functions. There's just one solution here given these boundary values. It's unique. But you might not see that in the complex notation. You might have an apparently different answer in your complex notation here. So anyway, once I know that, once I have thought this far, then I just put an A and a B here and then fit A and B to suit my purposes. And as you can see, I can do that because if I want 10 here along the, where phi is equal to 10, the argument 0 is in the allowed angles for this branch cut of the argument, right? I can have 0 angle in there, it's in there. And so if there's 0 here, I put that 0. So it has to, I want 10, A times 0 plus B, so B is 10. And then when phi is equal to 0, that's angle minus pi over 2, right? But I don't do minus pi over 2 because minus pi over 2 isn't in this branch of the argument. However, what is there is 3 pi over 2, or 6 pi over 4. That's the angle. And so I put that here, and that tells me that A is minus 20 over 3 pi. And you can check, unless I've made if I've made an arithmetic mistake, then speak up, let me know. It's possible. I do think, though, this is going to work then. So when you put in 0, you get 10, good. And when you put in 3 pi over 2, you get what? You get the 3 pi's cancel, minus 20 over 2 is minus 10 plus 10 is 0, good, it checks. And then if I plug in 0, the value of the solution at 0, I think is 5/3. Anybody agree, disagree? I see one agreeing. That's good. Oh, good. But you couldn't figure out why? No. Oh, okay. If someone online agrees, we must be right. Well, yeah, Wolfram is,
Is he capable of making mistakes?
That's a good question. We should ask him.
Is he dead?
seems like this may be a waste of our time, but
Moving on from Naruto.
If your input in English, try to click come on.
are you? All right. Sorry.
I think that means he said no. Of universal computation.
Oh, and that's all I got. Well, this is it's not fun. You're having a blast. That is good. That is good.
So you're definitely not going to put any Cauchy integral formulas on the test, right? You're not going to put any of those type of problems. Like, there's not going to be like 15 of them, and that'll be the whole test. That's what you're not going to do, right?
Are you gonna
Reverse psychology.
You can't ask him that, and now you've undone the goodness of his.
I know, but it wasn't even a word.
The fact that you're asking that question makes me happy. But yes, I would like. I mean, I wouldn't. That would be a fun test to grade, right? Just here's 20 Cauchy integral formula questions, right? That wouldn't be bad, would it? Let's see here. So you guys are good on those, is what I'm hearing? No?
No, this is like the worst part of the quiz.
Aha! I see what you're doing there. Where'd my book go?
So hard, I can never figure them out.
Let's see here.
They don't challenge you or stimulate you at all.
So in the time that remains, which those boundary value problems are just too they're so easy. Yeah. Just make the test just about that, right? No, wait a minute. I forgot this. I've forgotten the method of psychology that we're using here. I lost track. It's like Inception, but for test planning. But. So of course I hope you have also noticed that the answers to much of number 1 from section 4.4 are already from last year's homework, but that doesn't change the fact that you should think through them. So this one, z to the n over z minus 1. How do we do this one? So clearly, the first things first is to understand the curve and understand the singularities, right? Those are the two things that you have to kind of compare. This has singularity z not equals to 1 blows up, right? And, oh man, maybe I should just not even bother taping review days. Let's see here. Probably. So what? So what do we want? We want 2 pi I f of z naught, right? Cauchy's integral formula, m equals 0. But of course, f of z is what? Z to the n here, so this is just 0. Am I right? Am I wrong? No?
No, that's what I got.
Okay, good. So that was A. I like the look of E. E looks interesting. I'm not sure I signed this one or not, but I could have. Let's see your unit circle, modulus of z equals to 1. You got yourself e to the z over z to the m dz. I didn't assign it. Yeah, that's fine. We can still do it. Oh, I didn't do A? Well,
Oh, no.
these are, I think these are all good, except for the one that was, one of these I talked myself into, I feel like there was a difference in printing, and I have a book, maybe not this one, but another copy of Gamelin I had. One of these examples had the singularity on the curve. If the singularity is on the curve itself, it's a typo. That shouldn't happen, all right? We have no theorem to deal with that at the moment. Okay, so anyway, it will happen later in the course that we'll have a way of dealing with. We can have a singularity on the curve, but we have to kind of like in an approaching sense, we make a little loop around it and let the loop shrink to 0, and that is a meaningful calculation we do later. But we haven't done that yet, obviously. Okay, so this one, you've got well, this is not m equals 0. This is m equals to quote unquote m equals to what? Tell you what, let me make this k. There, it's better. So if I make this k, m is equal to, how to say this? K minus 1, right? And clearly the unit circle has the singularity 0 inside it, right? So we can apply Cauchy's integral formula. And what would it say? It would say 2 pi I, the k minus 1th integral, derivative rather, of e to z. Well, hey, that wasn't too bad. I was worried. I'm like, oh man, I have to differentiate this thing k minus 1-fold times. This could be a drag. Well, it's the exponential, so this is just 2 pi I. So I know this is very, very difficult, so I will try not to put this on the test. Is that right, Nathan?
Right. So you actually have a over k minus 1 factor.
Ooh, very good. See, where does it?
Like it's easy to make little mistakes like that.
That is true, and if I make this a lot of points, then you'd lose a lot of points for that too, wouldn't you? Oh my goodness. Yeah, that would be sad. Thank you. Joking aside, though, of course I will put some Cauchy integral formulas questions on the test. I think it's good. It's an easy way for me to test whether or not you know where like complex sine is 0, for example. Oh, we're not quite there yet, are we? If I put sine in the denominator, it's troubling, isn't it? Yeah. Okay, but so you guys are good on these ones. Number 4 of section 2, did you guys get that one? It kind of tells you the truth of the end. Basically, he tries to walk you through why the log of z minus z plus z squared minus 1, right, is the antiderivative for the given function, right? He says it's a primitive. So he's like, if you differentiate this with respect to z, you get what? You get 1 over the square root of z squared minus 1, where gamma is the path from minus 2i to 2i, does he say? Minus 2i to 2i counterclockwise. And and then what were we supposed to do? We were supposed to evaluate that integral in the case that it's an entire circle. Are we supposed to do two things? We're supposed to. First of all, we're supposed to calculate the integral when it's a half circle, and then when it's an entire circle. Now, how would you do the entire circle calculation? So for part C, if we integrate, if this is gamma, right, we just have to integrate so we just have to calculate what's the log of what? The ending point is 2i, so log of what? 2i plus the square root. Now, what's 2i squared is what? Minus 4? So this is minus 5, am I right? No? Yes?
Yeah, that's right.
And then log of what? This one would be minus 2i. Again, plus the square root of minus 5. Now that is going to be the natural log of the modulus of, is it 3? These are principal logarithms, yeah? Oh. This is a scalar multiple of I, right? Yeah, so it's pi over 2. This is also pi over 2? This is 0. Is this 0?
No, that'd be negative pi over 2.
This one's negative pi over 2?
No.
That one's this one's minus pi over 2?
Yeah.
And so this.
That's a multiple of, or is it?
That's what I'm wondering, yeah. Because unless I made a.
Negative 2i plus I times square root of 5. So.
Yeah, I think it's still positive. I think, yeah, it looks to me like it's 0. I mean, I could be wrong, but. Oh, yay. Okay, well, here's why it's 0.
Do we believe that though?
Part of the reason I assigned you guys problems that have answers in the back of the book is so you can check your work, yeah. I just forgot this had an answer in the back of the book. Now, so to get the whole circle, what would you do? If I recall correctly, I think the trouble is this antiderivative, does it fail like over here? Where does it fail? I think he tells us earlier the negative real axis, right? Is that right?
Yeah, I think
So z plus square root of z squared minus 1 omits the negative real axis. That is, the range of the function on D does not include any of the values on. Oh. Well, hold the phone. The answer for D is also 0. No? It's not, is it? I mean, if I understand this correctly, what he's saying, pi I, really? Oh, that's troubling. How can that be? Do you guys, anybody get it? Did anyone get that here? Why that's pi I? Section 4.2, number 4. Oh, there's no answer for this one. Well, I would think that the answer here should be 0 if I understand what's said before correctly. What's said before here is that this does not hit. This doesn't hit. This is, well, let me just put it more succinctly. This is an element of the slit complex plane, all right? Those values never hit the negative real axis, right? Which means that that function has domain the punctured plane, I think. Oh, but it's the punctured plane, right? There still could be, well, z equals 0 is not a problem either. No, I'm sorry. It's an element in here, so it's not 0. The point is that this is actually if I have read this carefully, if I've read this properly, this is an antiderivative for this function on the whole complex plane. Even though it's built with a principal logarithm, the input to the thing puts the values of that expression, z plus square root of z squared minus 1, into the slit complex plane. And so, Um, so what then? So I think that the D has to also be 0, but I feel like C should not be 0. C should be like, maybe we made a mistake here. I'd like to believe we've made a mistake here somewhere. I just don't see it. So at the moment, it looks to me like C and D are both 0. So now, did you guys understand the questions about Leovol's theorem? The answer, the hint in the back of the book is very, if you just follow that, it's quite natural, right? Do you think you could solve the fundamental theorem of algebra question if I was asked that on the test? Can you bound simple functions? Like suppose you wanted to bound, 1 over z squared plus 4 on the circle z equals to 3. What would you do? Mm-hmm. Right, but this one we have to do what? Modulus of z squared minus 4, right? I mean, technically the square is inside to start with, but then we move it outside, right? So there's this reverse triangle inequality thing, or whatever you want to call it, this guy. So if I make the denominator larger, then it makes, excuse me, if I make the denominator smaller, it makes the fraction larger, right? And so then it depends on, if that was 3, this is what? Yeah.
So does that work if you have more than 2 terms?
No.
Okay.
No. As soon as you get to 3, it's troubling. So for something like this, I know that's where I was going. So this one, for example, I can still handle because this would be, equal to, first of all, 1 over the modulus of z plus 2. Oh, sorry. Because I can factor that, right? So if you can factor it, then if you can factor the polynomial, then you can attack the factors separately, each one attacking it with the funny inequality, right? Like, so if that's 3, what's that? 1/2. Thanks. Yeah. But that's why that result, that technical lemma, which I give to you from Churchill, in that fundamental theorem of algebra problem, is so precious, is that gives you a tool to replace an nth order polynomial with just some constant times the nth power, the power of the highest term raised to the radius. I mean, the result of that problem in Churchill is that if you have a polynomial of z, then you can find that the modulus of that is greater than or equal to some constant m times r to the n for modulus of z greater than or equal to r, or something like that. That's the result, which is pretty awesome because it means that these kinds of things can be supplanted with some more general argument. But that's built over the geometric series in a rather kind of tricky argument. I do actually want you to be able to do arguments like this and that for simple examples. I don't expect you to just pull this from the thin air just yet. A little bit later, I'll give you the freedom to do that. But where did I put my phone? Oh no, 12:55? Ah, all right, well. I think I should move the test to next Monday. You guys don't know anything from what I can see in here. No? I can leave it Friday. All right, all right.
We know Yeah.
So Friday it is then, but
What is a weekend? Isn't that like the
Friday it is,
time
but
to, like-
I am not going to cover new material Wednesday. Wednesday we are going to spend another day just going over. Well, Wednesday. What's that? Oh, yeah. Yay.
Shove him to the rescue. Wonder Woman.
You should go slower and zoom in.
I don't know how to zoom.
Oh, well, that explains certain past.
I would move this thing back and forth.
I should make you guys watch the Calc 3 people. They know how to do it. They got some really nice videos. They zoom in. I was all over the place. They're like following me, zooming in on calculations, all kinds of stuff. I mean, it's really something.
Well, how do you zoom? You never taught me.
It's this thing here. I really wish it said zoom, but unfortunately, if it said zoom.
I didn't know if that was like the click to get
Actually, what am I saying? The video can't see it. See right here where it says zoom.
Wait, it says zoom?
No, it doesn't.
Wait, you want me to hit power now?
Yeah, you can hit power.